let's continue. Our first speaker is Haonan Zhang, and he will talk on Bohnenblust Hille inequalities and low-degree learning. Please.
Okay, thank you very much. Many thanks to the organizers for the kind invitation, and also many thanks to the organizers for organizing this wonderful conference as well as a program. So this is based on joint work with Alexander Volleberg and Joseph Slot. The topic is about a very classical harmonic analysis inequality named after Bohnenblust and Hille, together with some recent applications to the learning theory. And this inequality actually has a very long history. Let me give you a very brief review. So it starts around 1913. There is a problem by Boch asking about the convergence of a Dirichlet series. So since this is not the focus of today's talk, I will skip the details. And the solution in solving this problem, the so-called Boch-Strieber problem, along the way, the Bohnenblust and Hille, they discover a family of inequalities in 1931. This is the so-called Bohnenblust Hille inequality. There are several variants of this inequality. The one that I'm interested in here is the polynomial version. In contrast, there is also a D-linear version of BH inequality. So basically, this inequality was motivated by a work by Littlewood in 1930, the so-called Littlewood forces inequality for bilinear forms. Now let's look at this inequality. This is a very simple inequality relating a function and this Fourier transform. Okay? Some LP norms of a function and LP norm, some LQ norm of the Fourier transform. And this may remind you the basic Hausdorff-Young inequality. So here I'm considering a function on the circle group, and I have a Fourier expansion. Then we know by Pascal-Plancher identity the little L2 norm of a Fourier coefficient is the same as the L2 norm of a function when you equip it with a normalized uniform probability measure on the circle group. And you also know by definition that L infinity norm of your Fourier coefficient is bounded by L1 norm of your function. Then by complex interpolation, you know that Fourier transform is contraction from LP to LP prime, where this P is between 1 and 2, and the P prime is the conjugate of P, so P prime will be from 2 to infinity. And this is a classical Hausdorff-Young inequality. Well, this Bohnenblust Hille inequality, or we just call BH inequality in the following for short, says something the other way around. On the left-hand side, you have some little LP norm of your Fourier coefficient, but this P here is strictly smaller than 2. Okay, so here this P prime is bigger than or equal to 2. Well, on the right-hand side, you have the L infinity norm of your function, but Hausdorff-Young here you have LP norm with P that is not larger than 2. So it's kind of the reverse in the other direction of the Hausdorff-Young. So you know that this could not happen in general, and it happens when your function has some special structure. And actually, the condition here is that a function here is an analytic polynomial that has degree at most D. Here, D is fixed. So on the left-hand side, you have the LP norm. This P is this 2D over D plus 1. So this is Hausdorff-Young. This is the BH. BH says that this is 2D over D plus 1. This can be bounded. On the right-hand side, you have a function, and you have L infinity norm with a constant. This CD here is independent dimension. Okay? But certainly this function here is not everything. It is an analytic polynomial whose degree is at most fixed D. So that is a BH inequality. So at that time, this control of this constant, so at the first proof, this constant is kind of d to the log d, which is d to the d, which is very, very large. And later on, people find the applications of this inequality in some other harmonic analysis problem or or the functional analysis problems. And the breakthrough was made in around 2011. People show that this constant is at most c to the d, so it's kind of exponential growth, which is very important in determining some optimal behavior, for example, the Seaton constant. The current best known upper bound is c to the power square root of d log d around 2014. So this is kind of sub-exponential growth in d, and this is important in determining the optimal behavior of the, for example, the Bohr radius problems. So there are also some other applications of this inequality in classical harmonic analysis or functional analysis, as well as some other areas. So a good reference will be a recent book by Define and his collaborators, the Dirichlet series and homomorphic function in high dimension. So this is kind of the classical story, and having this is very natural to ask a variant of this inequality for other groups. We know Hausdorff-Young is valid for more general groups, okay, or quantum groups. So this BH inequality looks very reasonable, and the story is that there are such variants of BH inequality for this very simple group, this cyclic group of order 2, or the so-called discrete hypercube. And having this, you can also ask how about the cyclic group of general order. So this is a question that I asked myself when I first see this inequality for this two-point space. I tried a little bit and didn't get anything. I also do not have too much motivation apart from this classical story. But a very interesting thing is some recent progress on the quantum counterpart. Instead of asking this inequality for the two-point space or the bit system, you can ask the same question for the qubit system or the 2x2 matrices. And you can continue asking question about the k-by-k matrices, and this is a so-called QDIT system. It turns out that in order to solve this problem for QDIT system, you need to come back to the cyclic group of order k. Okay? So this is kind of the plan of today's talk. But as the title suggests, there are some interesting applications in learning theory, which is kind of the motivation in recent years. So basically, the problem is as follows. You have a function on this n-dimensional discrete hypercube. Sorry. So this plus minus 1 to the n, you have a function living on this space. Very often you will see such functions that it takes values in plus minus 1 as well. These are so-called Boolean functions, which are very important in theoretical computer science. Then the question is, how many samples do we need to learn such functions? Okay. And in general, this is a very difficult problem, and you are allowed to impose certain structures on the functions. Say the function has small complexity, and there are many ways to quantify this complexity, and here in this talk, we will consider the degree here. Okay? So roughly speaking, we want to learn function that has small degree with a small number of random queries, which I will make this rigorous later. And this is a question in the classical part. In the quantum world, you ask the same question for matrices. Okay, so roughly this is a motivation. So let me start with some notations. I have a function on the classical Boolean cube. I can take a real value or complex values. Then, in any case, I have a free expansion, which means any function is a linear combination, unique linear combination of these characters of the group. Here, the character is denoted by chi-s, where this s here is the subset of first n positive integers. Then each chi-s is a character that takes n-dimensional vector x to product its coordinates xj, where j belongs to s. Since this vector x lives in the n-dimensional Boolean cube, so each coordinate xj is either plus 1 or minus 1. So xj squared is always equal to 1. This is always a multi-affine polynomial. in n variables. Okay? In the quantum counterpart, instead you consider matrices that is of size 2 to the n by 2 to the n. You also have a Fourier expansion or Pauli expansion. And in this case, you replace the characters by the tensor product of Pauli matrices. I will denote by sigma naught, sigma 1, 2, 3, the Pauli matrices, with sigma naught being the identity. Then sigma 1, 2, 3 will be the 3 Pauli matrices satisfying certain anti-commuting relations. Then the tensor product sigma s is simply the tensor product of all the sigma sj, where each sj belongs to 0, 1, or 2, or 3. So this way I can define my Pauli expansion or Fourier expansion, and this can be considered as some non-commutative analog of the non-commutative polynomial. Then we say that in the classical setting, the function is of degree d if it is degree d polynomial. Okay. In other words, the Fourier expansion, Fourier coefficient vanishes whenever the cardinality of S is bigger than d. In the quantum setting, you define the degree in a similar way. You just count how many non-identity Pauli matrices you have. So you say that this matrix A has degree d if the Fourier coefficient vanishes whenever the length of this small s is bigger than d. This small s is a vector, n-dimensional vector, with each entry being 0, 1, 2, 3. So its length is defined to be the number of non-zero entries. So just count how many sigma 1, sigma 2, sigma 3 in this tensor product. And in the Fourier analysis, we have the Parseval identity, Parseval-Plancherel identity, which means in this case, if you equip the Boolean cube with a uniform probability measure, then the little L2 norm of your Fourier coefficient coincides with the L2 norm of your function, which is also the case in the quantum setting if you equate with a normalized trace that defines the normalized LP Sharpton P norm. In particular, this sigma s, the Pauli matrices, the tensor product of Pauli matrices, they form also normal basis with respect to the inner product induced by this normalized trace. So you still have the Parseval identity. Okay. Any questions? Then let's come back to this learning model. I want to learn the family of low-degree functions. Okay, low-degree bounded functions. So this is a class of fn smaller or equal to d. This is a function living on the n-dimensional discrete hypercube that is uniformly bounded, and the degree is uniformly bounded by d. Okay, let me first read this random Curie model. You fix epsilon and delta, that is a small positive number. Then you consider the smallest capital N, the positive integer, such that the following holds. You take any function in this class, you take any ID random variables that are uniformly distributed on the n-dimensional Boolean cube, together with a Curie, which will be random. Then you need to construct a random function, say h, such that the probability, the little L2 norm, the L2 norm of f and h, f minus h is small, is at least of probability 1 minus delta. So what does this mean? This means I have a function, but I will not tell you. Say that this is a function that is defined on the 50 plus minus 1 to the dimension 50. Say that we have 50 people here. And each of you will give me a plus minus 1, say x1, x2, x3. So you will give me one string, say 1, 1, 1, 1, 1. Then I will tell you the value of this function. Okay, see, this function is very simple. fx is simply x1, but you don't know. So when you give me this string of 1, 1, 1, 1, I will tell you that the value of this function is plus 1. If you, next time, if you give me negative 1, negative 1, negative 1, I will tell you the value of this function is negative 1. So each time you choose between plus minus 1 with equal probability, independent of your previous choices. The question is, how many times do you need to use this information to approximate this unknown function? And my choice of this function is from the class of these low-degree bounded functions. So maybe this time you get a good guess for this fx is equal to x1, but next time you also need to maybe x1, x2, and xd. Okay? So this is this capital N, or the so-called Curie complexity, and the question is, what is this Curie complexity number? It will certainly depend on epsilon. Epsilon is your accuracy number, accuracy parameter. Delta is the confidence. And it will also depend on this d and n. And my question is that when n goes to infinity, I hope that this Curie complexity will not grow too fast. So you want to use a very small number of random Curies to recover this unknown function efficiently. That is the model. Any questions? Okay, it turns out to solve this problem, you need this BH inequality that we mentioned from the very beginning. So the first untrivial result is due to linear Mason-Nissan in 1993. They have a very simple low-grade algorithm telling you that there is an upper bound of this capital N. Since I'm only interested in this dependence on dimension, this upper bound is essentially n to the d log of n. And the proof, this algorithm is very simple. You want to learn this unknown function, okay? And it will, and the idea is to not to learn this function directly. Instead, they want to learn the free coefficients, because the Parseval identity tells you that if you want to learn the function in L2 norm, is the same as learning its free coefficients in the little L2 norm. Okay. Then what can you do? What you know is this family of random Curies, and you can use these random Curies to recover the free coefficients as follows. So how do you recover, how do you compute the free coefficient? Free coefficient is the inner product of a function f and the character chi s. And this Chernoff bounding probability tells you that with high probability, as long as this capital N here is very big, then you can recover the real free coefficients from these empirical free coefficients with high probability. How this empirical free coefficient is defined? You just look at the random Curies f of xj, you multiply by ks of xj, then you know that the expectation is exactly the real free coefficient. So if you have n number of this quantity, since they are just the sum of ID random variables, then Charles bound tells you that as long as capital N is big enough, then with high probability, this empirical free coefficient is very close to the real free coefficient. Then you repeat the same procedure for all the possible non-zero free coefficients. How many non-zero free coefficients you may have? That is the sum of n choose j, with j from 0 to d, because the function has low degree d. So in total, this is n to the d non-zero free coefficients, and that is why you have n to the d in your final answer, because this is essentially the number of your parameters. So in some sense, this was believed to be optimal, because you do have n to the d many non-zero free coefficients, but the answer is not. So in 2021, there is this improvement from n to the d to the power to n to the d minus 1. So this is a very small improvement, but it's already kind of surprising. But what is more surprising is the following result by Askanazis and Ivanisvili, saying that you only need a logarithmic of n random Curies, so you can remove this polynomial dependence completely. And the only new gradient in the proof is this Bohnenblust Hille inequality. By the way, the same author and the Streck also show that the log of n is optimal. So for this Curie complexity, its dependence on dimension is not very clear. It's just the log of n. But how can you go from n to the d log of n to log of n using this BH inequality? The reason is as follows. You have a lot of non-zero free coefficients, say n to the d, but their little L2 sum is bounded by 1, because the function is bounded. So actually, many of the non-zero free coefficients are actually very small. So suppose that we have this 1 over 10. So we set up a threshold. We look at the free coefficients. If it is absolute value is bigger than 0.1, will be influential. But the number of such influential free coefficients is very small. It is at most 100. Okay? And how about the other ones? For the non-influential free coefficients, which are those absolute values at most 0.1, they may have n to the d. The quantity might be n to the b because the total sum is n to the d. So if I find one non-zero free coefficients, say 1 over 1,000, so maybe I can simply forget about this free coefficient. So what I gain is that I can reduce the sample complexity by number 1. What I lose is a very small accuracy. So the question is whether I can forget about all the non-influential free coefficients. Then what I will gain is a big improvement in the sample complexity. I can just reduce n to the d to a constant number. But what I will lose, it might be something very huge. So I want to compute this cost of throwing away all these non-influential free coefficients. So I will need to estimate the L2 sum of the non-zero free coefficients whose absolute value is at most, for example, 1 over 10. You know this is bounded by 1 because the function that is uniformly bounded by 1, but this is not enough. You want this number to be as small as possible. What you can do is to divide this 2 by p and 2 minus p. So instead of considering this L2 sum, I can simply consider the LP sum with p strictly smaller than 2. Here I use the fact that all the free coefficients here is at most 1 over 10. Okay? Then what I need is a control of this letter LP sum of the free coefficients. P here is strictly smaller than 2. I hope that the upper bound is something that is independent dimension, which is exactly the Bohnenblust Hille inequality here. Okay? And the good thing is that we do have this inequality already in 2001 by Bly, saying that if you consider function on the n-dimensional Boolean cube, if it is degree at most d, that is fixed, then for any dimension n, you have the same BH inequality. On the left-hand side, you have the LP norm of your free coefficient. On the right-hand side, you have L infinity norm of your function with a constant CD here that is independent dimension. Okay? And to catch the best known bound in the torus case, this inequality was revisited by Defan-Mastier and Paris in 2019 to obtain this sub-exponential dependence upper bound c to the power square root of d log. Okay? So this is kind of the story on the Boolean cube. Then in 2022, we conjecture a qubit version of this inequality. The statement is very simple. You have 2 to the n by 2 to the matrix. You define the free coefficients and the degree as we did from the very beginning. You ask the same inequality here. On the left-hand side, you have the LP norm, little LP norm of free coefficient. On the right-hand side, you have the operator norm of your function. You expect the constant here to be, again, independent dimension n here. Okay, the exponent here is also 2d over d plus 1, if it is true. This was a conjecture in 2022, and it was conjectured before it was actually resolved. So when we put this preprint in the archive, we received a message from people from quantum computation, Stan Huang, Stan Chen, and John Prisco, saying that they already solved this problem in a preprint that was not public at that time. So in their in order to learn the predict arbitrary quantum process, this is the title of their paper, they also need some inequality of this type. And they actually prove this inequality with a constant of order d to the d. The proof is very technical, so we try to find a simpler proof. And this is a work joined with Volleberg. We show that you can improve this constant to exponential growth. And actually, we find what we call a reduction method that reduces many problems on the qubit systems to the classical Boolean cubes. So what we really proved is that as long as this inequality holds for the two-point space of Boolean cube, then the inequality for the qubit system also holds. with an additional factor of 3 to the d. The factor 3 here is because we have 3 polymatrices. So how does the proof work? The idea of the proof can be explained in the following way. It's actually not very difficult. If you want to prove this inequality for matrices, say A, and the idea is to find a classical function depending on this A, let's call it f of A, that is living on some dimension of the classical Boolean cube, such that this chain of inequality holds. So I have 3 inequalities here. The one in the middle is kind of known. It's just a classical Bayesian inequality for the Boolean cubes, so it comes over 3. The problem is to prove the left inequality and the right-hand side inequality. So what we need to do is to find the function fa. So on the right-hand side, the L infinity norm of fa is bounded from above by the operator norm of A. On the left, I want to bound the little LP norm of fa, free coefficient of fa from below by the little LP norm of the free coefficient of A. So you need to control the function and its free coefficients in 2 different directions. As long as you can do this with dimension-free constant, then you are done. And the good news is that you can really find such a function. And the key is essentially the anti-commutation relation of the polymatrices. Okay? So how can you do this? It is easy to control left-hand side or the right-hand side. Suppose that we want to prove right-hand side, then it's very natural to take fa. The value of fa at any point is the inner product of A with some density matrices. Then by duality, then you get the right-hand side inequality for free. Then you need to choose this density matrix suitably such that left-hand side inequality is satisfied as well. So how can you do this? Let me first tell you how this fa looks like. This map from A to fa is linear. So you only need to look at the monomials, say A that is of this type, of this form. A is some tensor product of polymatrices. And I'm only interested in the case when it has non-identity polymatrices. Sigma 1 may be here, or sigma 3 might be here. Okay, I highlight their position and which sigma 1 or 2 or 3 you choose. Then what is my fa? If A is on the n-qubit system, fa is not on the n-dimensional Boolean cube, but 3 n-dimensional Boolean cube. So how it is defined? Fa is defined on 3-dimensional Boolean cube. So I divided this 3n vector into 3 pieces. Each of them is n-dimensional subvector called x1, x2, x3. So let's take this very simple A, for example. Just look at this capital A. If it is very simple polynomial, identity sigma 1, tensor sigma 2, then how does fa looks like? Fa, A here is defined on M2 tensor 3. So fa will be defined on plus minus 1 to the 9. And this definition is as follows. fa, you have x1, 1, x1, 3, x2, 1, x2, 3, x3, 1, x3, 3. Okay? Then its value is as follows. It is also monomial. How is this monomial defined? You look at where you have non-identity polymatrices. So you have sigma 1 here. When you first see sigma 1, you look at the first subvector. If this sigma 1 appears in the second place, then you look at the second variable in the first subvector. So you have x1, 2. Here you have sigma 2. Then you look at the second subvector. If it appears in the third place, then you have x2, 3. But you also need an extra factor 3 to the power -2. So that depends on a monomial, the degree of this monomial, which is needed. So what we just show here is that there is a 1-1 correspondence between the free coefficients of A and the free coefficients of FA. They only differ up to a multiplicative constant, and this constant is uniformly bounded as long as your polynomial has low degree. So degree is uniform bounded. So you can always compare their little LP norm. Okay, then how do you prove this? Essentially prove the left-hand side inequality. How do you prove the right-hand side inequality? This depends on a clever choice of these row matrices. How does a row matrices look like? It is essentially a tensor product of density matrices. How do you define the term in the jth place? You only need 3 plus minus 1 scalars that appears in the jth place in the first subvector, second subvector, and the third subvector. And the definition here is given by the average of three projections, eigenprojections of the corresponding polymatrices and corresponding to the eigenvalue plus or minus 1. So essentially it is average of three eigenprojections of the three polymatrices, and which polymatrices you choose depends on these three numbers, whether they are plus, which eigenprojection you need to choose depends on these three plus minus 1 numbers, okay, roughly speaking. I will not talk about the technical details, just to give you a very simple observation. So why we need the anti-commutation relation here. If you have two matrices, the polymatrices that are anti-commutative, then you look at the spectral projection corresponding to sigma j. If you take the inner product of sigma I, this will be 0. So that's all that we need here. Okay? Then if you look at the inner product of these polymatrices and this average of eigenprojections, your input is a quantum monomial, and your your input is quantum variable, and the output will be exactly a classical variable. So when you take the tensor product, you will get this 1-1 correspondence between the quantum monomial and the classical monomial, roughly speaking. Okay, so this is kind of the story from a 2-point space to the 2x2 matrices. Then people ask what happens to the QD system. That is the case when you have K by K matrices. In the K by K matrices setting, you have the generalization of the polymatrices, the so-called Heisenberg wire basis, as a basis to define the free expansion. So how this is defined? This is defined in terms of the so-called shift operator and the clock operator. Shift operator, it means it shifts to the jth basis Ej to Ej plus 1, while the clock matrices maps Ej to omega to the j Ej. So essentially X looks like this. Z looks like this. So they are all case roots of identity matrices, and they satisfy certain anti-commutation relations. So using this to define the free expansion, you can ask the same question. And there is this learning problem which you should be able to solve using these BH inequalities for the QD system. Then to prove this inequality for QD system, you ask yourself whether you can reduce to the classical setting. And we have a similar picture here, but this time, left inequality and right inequality is true. What is open is one in the middle. Okay? So here, roughly speaking, we have this multiplicative cyclic group of order k. We assume here that k is prime, but this is not essential. Then for any matrix A, that is k to the n by k to the n matrices of low degree, we can find a classical function fa such that this chain inequality holds, but not the one in the middle. The one in the middle is the problem of classical harmonic analysis, which was not known at that time. So what we know are the cyclic group of order 2 and the torus case, which can be considered as some cyclical order infinity. So what we know are the two extreme cases. What is in between For k equals 3, for k equals 4, we don't know. But the proof of these two extreme cases are almost identical. So why the proof does not work? The proof does not work because of following. Because of some kind of dimension-free approximation equality was unknown. So if you repeat the same proof for k equal 2, k equal infinity case, what you can really prove is the following. You have a function, let's consider the k equals 3 case, 1 omega squared to the n. You define the free expansion, then what we want to prove is some little LP norm over free coefficients. You want to prove that this is bounded by the supreme norm of the function over the group. But what you can actually prove is the supreme norm over the convex hull of this group. Okay? So you want the supreme here to be over the product of these 3 points. But what you can prove here is the supreme over the product of these triangles. Okay? So what we need is some dimension-free estimate here. But why don't we have this problem in the classical setting? In the two extreme cases, when k is equals to 2, then these 3 points will be replaced by 2 points. Then the convex hull will be an interval. But my function here is multi-affine. We know that for a linear function, we know that for a linear function is a supremum over an interval is exactly the supremum over the extreme points. That is easy with constant 1. And with k equals infinity, the group is this circle. Well, it's a convex hull becomes this disk. But my polynomial is analytic, so this is nothing but the maximum modular principle. Again, with constant 1. So the problem is whether you can have such estimate for example, for these triangles. Okay? Some kind of generalized maximum modular principle or some dimension-free approximation. And the difficulty is that if you look at the dimension 1 case, n equals 1 case, just compare the supremum over this triangle and the supremum over these 3 points. It's not difficult to prove, but the problem is that the constant c here must be strictly bigger than 1. So you cannot tensorize. If you tensorize, you get a constant that blows up as n goes to infinity. So the difficulty is that you need to make use of the low degree assumption to prove such a dimension-free estimate. So that is kind of the new difficulty, and to overcome this, you need some kind of approximation idea stuff. So the story here, to summarize, is that we know how to reduce the problem k by k matrices to k points, or the single group order k. But if this result in the classical setting does not hold, then everything is meaningless. The good news is that this inequality is indeed true. So it's purely some classical approximation theorem. And as a consequence, you know this BH inequality for cyclic groups. Then you know the BH inequality for k by k matrices. Then you know the logarithmic learning in the QD observables, for QD, low degree QD observables. So all these problems are reduced to this dimension-free estimate in the classical harmonic analysis. Since I don't have too much time, let me just conclude with some questions and remarks. What people are interested in is this best dependence. Best depends on the degree of this BH constant. So here I formulate the problem for the 2-point space or for the cyclic group order 2. We know the best known upper bound in general is c to the power square root of d log d. And some people conjecture that it is polynomial in d. But some people even conjecture that it's a universal constant, say 2, because we don't have counterexamples. Even for 2, we don't have lower bound. So it might be that the upper bound is indeed independent of d. Let me finish with one recent result. where people consider this problem for completely bounded norms. What it means is that on the left-hand side, you still have little LP norm of your free coefficients, while on the right-hand side, instead of considering L infinite norm, you consider CB norm, which means you replace the variables, classical variables, by contractions in any B of H. You take the supernorm, this is a CB norm. So this is a much larger upper bound. So the inequality should be weaker. But the advantage that the constant looks nicer, this is constant 1, which is optimal. So the result somehow looks more beautiful. So with this, I want to conclude my talk, and thank you very much.